Let us solve one problem on symmetrical components. So, figure shows a three-phase balanced load. A star-connected load. This is neutral point, and we have three-phase four-wire supply, and supply is also balanced. So we have balanced supply, balanced load. So four-wire supply means RYB, three phases RYB, and one neutral wire is also there. So obviously neutral will be connected with the neutral of the load, and load is star connected, so we have one neutral point. Okay. So it says that the current in the lines are 60 ampere. The magnitudes of the current in the lines are 60 ampere, and the supply is balanced. So we know that the currents may be written as IR. Let us take IR as reference. So IR will be 60 ampere. Let us take as reference, so angle 0. Is not it? So what about IY and IB? Balance supply means magnitudes are equal, and phase displacement between the two phases is 120. So same magnitude, 60 angle minus 120 degree. Is not it? What about B phase? 60 plus, or okay, write first 240 degree. If you want to write plus, okay, the same can be written as 60 angle 120 degree. This you want, right? This is same as we have 360 degree as its period. So similarly, you can write this as 60 angle 240 degree. Is not it? Minus 120. Okay. So when fuses are not removed, we have to evaluate the symmetrical components of the line currents. Write here line currents. For the two cases, see, two fuses are there in Y phase and B phase. So two cases are before the removal of fuses and after the removal of fuses. So before the removal of fuses, supply is balanced. We have balanced currents in all the three phases. Balanced currents means the algebraic sum of all these three currents will be 0. Is not it? So no current will be there in the neutral unless condition is unbalanced by anyhow. So one reason may be if you are removing these two fuses or any one fuse, in that case the algebraic sum of all the three currents will not be 0, because once fuse is removed, so no current will flow in this phase. Is not it? It will be open conductor. Is not it? So second case is when the two fuses in Y and B phases are removed. In that case, current in Y phase will be 0 and no path. Current in B phase will be 0 and no path. Only current in R phase will be there, as we have return path. Otherwise, if we don't have any return path, so circuit will not complete. So in that case, no current will be there. We will discuss later. So for present case, we have neutral path. So although the fuses in two phases, Y and B phases have been removed, even though the current in this will flow, R phase will flow, as we have return path. Is not it? Okay. So for case 1, when fuses are not removed, so in this case the supply is balanced, condition is balanced. So for balanced condition, zero sequence currents will be 0. These sequence currents, negative or zero sequence currents, are non-zero only when condition is unbalanced. When condition is balanced, in that case, there will not be any existence of such currents, negative sequence currents and positive sequence currents. Okay, we can prove it. So yesterday, we have seen that the sequence currents IR0, IR1 and IR2 may be retained in terms of phase currents IR, IY, IB. Let us write here IR, IY and IB. So take your notes from notebook. Take me the values 111, alpha square and 1 alpha square. Okay, so we know all these three phases. The currents in the three lines, R lines, R phase, Y phase and B phase. We have, right? We have all these three phases. So we may write this phasor, this phasor, this phasor. So conceptually, as we know that for balanced condition, zero sequence components and negative sequence components should be zero. So just check it. We will check whether coming out to be zero or not. Only positive sequence component will exist, and that will be same as these IR, IY, IB. So let us check. Then after that we will check for the unbalanced condition. So for case 1, when condition is balanced, we may write IR0. Remember, all the zero sequence components are equal in magnitude, having same phase. Phase displacement between zero sequence components is zero. Magnitudes of the all sequence components are is equal. So we may write IR0 is equal to IY0 is equal to IB0. Is not it? Yes. Are you reading it out? Yes. So this can be written as IR from here 111 multiply with this. Okay, we have missed 1 over 3. Is not it? Just check your notebook. Yes. 1 by 3 is there, right? So IR0 will be nothing but 1/3 of IR phasor plus IY phasor plus IB phasor. So write the values. Put the values. So IR is this one, 60 angle 0, plus IY is 60 angle 240 degree, plus this is 60 angle 120 degree. So this can be written as 1/3 60 angle 0 degree plus this is alpha square, is not it? Yes. So we may write 60 angle 0 degree times alpha square plus this can be written as 60 angle 0 degree times alpha. So take 60 angle 0 degree as common. So we will have 1/3 times 60 angle 0 degree 1 plus alpha square plus alpha. So yesterday we have seen that 1 plus alpha square is 0. So 0 into something is equal to 0 ampere. It must be 0 as condition is balanced. So for balanced condition we can observe that the zero sequence components of the currents in three phases is 0, are 0. So this is positive, this is zero sequence component of the current in R phase, zero sequence component of current in Y phase, zero sequence component of current in B phase. So in all the three phases, this component, zero sequence component will be 0. Why? You know the reason, right? Okay, now check for the negative sequence component, that is IR2, IY2 and IB2. So what is relation for I? Okay, first check for negative, then we will check for positive. As we know that these two components are 0, only this will be non-zero. So first check for IR2. So IR2 can be written as, just write here. Have you noted down this? Okay, so just write it. Negative sequence component IR2 is equal to, this IR2 can be written as 1 into IR plus alpha square IY. So write down IR phasor plus alpha square IY plus alpha times I. From this we may write IR2 is equal to this row multiplied with this column. So we have this. What is the value of IR? 60 angle 0 degree. Alpha square is nothing but 1 angle 240, right? Into IY is 60 angle 10 mean plus 240 plus alpha is 1 angle 120 degree, is not it, into IB is
60 into 120.
120. Okay. So this can be written as 60 into 0 degree.
So 1 by 3. 1 by 3.
Okay, 1 by 3 is also there. Yes. 1 by 3 is there. I am writing here 1 upon 3. So just write 1 upon 3 equal to 1 upon 3 60 angle 0 plus 60 angle 0, and this will be 240 plus 240 480. Subtract the period 360 degree. That will be 120. Okay. So 120 is nothing but alpha. 1 angle 120 is alpha plus 60 angle 0 into angle is 120. That is alpha square. Note it. So this will be alpha square. So this will be 1 upon 3 into 60 angle 0 degree. Take common, and here you will get 1 plus alpha plus here alpha square. So this will be 0. Is not it? Are you getting this or not? So we have seen that negative sequence component of current in R phase is 0, but yet we have not checked in Y phase and B phase. But we know how to write the current in Y phase and B phase once knowing the current in the reference phase, that is R phase. Yes. Remember this. This is negative. So if our sequence is RYB, so for this sequence will be, say this is R, so this will be Y and this will be B for negative, is not it?
Yes, sir.
This sequence is RBY, opposite to that of the original one. So negative phase sequence is just opposite to that of the positive one, original phasor, right? So if you know this R, you want Y, so that will be multiplied with alpha. If you want to write for B, then multiplied with alpha square. Okay. So you know IR2. So what about IY2? IY2 will be equal to alpha IR2. Yesterday we have discussed this, right?
Yes.
So IR2 is 0. So whether alpha or alpha square, that will be 0, is not it?
Yes.
So okay, you may write into 0, that is 0 ampere. Similarly, IB2 will be equal to alpha square IR2 is equal to alpha square into 0, is not it?
Yes. 0.
Is equal to 0. So what we have seen, that for balanced condition, as supply is balanced, loads are also balanced, so condition is balanced. For this case, zero sequence components and negative sequence components will be 0. They will not exist. Only positive sequence component will exist. So let us check for positive sequence components, right? So for using this relation, we are going to write IR1. So IR1 will be 1/3 of IR. Okay. So 1/3 is written here, IR plus alpha IY, is not it?
Yes.
And alpha square?
IP.
Okay. So what is IR?
60,
IR is this, and alpha is 120. So I am writing here 120. Just write fresh one. I am editing here. Don't edit the previous one. Write fresh one. Alpha square. So alpha square will be, this is IB, is not it?
Yes.
So this will be 240. 240. Okay. So 60 degree, and this is 240 plus 120, that is 360 or 0.
Yes.
So same phase.
Yes.
So this will be 60 angle 0. What about this? So 240 plus 120, 360 again. So rotating any phasor by 360 degree means you are getting same position, right? So this will be again, or you may write this is alpha square, so alpha cube is 1 by anyhow, right? Similarly here, this is alpha square, so alpha into alpha square, alpha cube, that is 1. So you will get this only, right? So you are getting 1 plus 2 plus 3, 3 times of this 1/3 get cancelled. So finally you will write
60.
What you will write?
60 angle 0.
60 angle 0 degree ampere. This is same as that. What you wrote? IR1, is not it?
Yes, sir.
So this is coming out to be same as that of IR. Just check it. Is not it?
Yes.
So write IY1. So IY1 will be for positive sequence components. The sequence is reversed to that of negative. So suppose this is R, this is Y, this is B. This is R, then Y, this is B. Is not it? For positive sequence components. So you know IR1. Now you want to write IY1. So IY1 will be,
Alpha square.
this is R, so 120, 120. Alpha square, is not it? So alpha square this. So alpha square this. Alpha square is having angle 240. Magnitude unity.
Yes, sir.
So you will get, this is 60. So you will get 60. Okay, write first.
60
1 angle 240 degree and this is 60 angle 0 degree. So this you will get magnitude as 60 into 1 as 60 and this will be 240 ampere. Is not it? This is coming out to be same as that of IY. Just take it. This IY.
Yes, sir.
It's not it. So next write down for IB1. Positive sequence component of current in B phase. And in B phase, just you will obtain by rotating these phasors by 120 degrees. That is multiplying this phasor by alpha. So write here alpha I. This was IR1. This is also IR1. Is not it?
Yes, sir.
So multiplying it with alpha. Alpha is 1 angle 120 degree. Multiply it with
60
IR1, that is 60 angle 0 degree. So this is nothing but
60 angle 120.
coming out to be same as that of IB. Just check. Is not it? So we can conclude that for balanced condition, zero sequence components and negative sequence components of the currents in the three lines will be zero. Only positive sequence components will exist and that will be equal to the original current. Is not it? Basically, the sequence components are the mathematical components of the original currents in the three lines. So if two components are coming out to be zero, so the single component that will be obviously same as that of the original component, is not it? Now come to the unbalanced condition, that is case 2, when fuses have been removed. Once fuses have been removed, so condition will be balanced or unbalanced? Unbalanced. Okay. So unbalanced, and you may write in this case IR will be same as earlier. See, what was that? 60 angle 0 degree. What about IY? Now, if for second case, 0 in here, no path. Is not it? And what about IB?
0.
This is also 0. Now for second case, we have IR as original one, as we have not disturbed, and we have provided return path. But for IY and IB, path is not there, as we have removed the fuses. So these currents will not flow, although supply is there, but path must be there, is not it? So condition is unbalanced because sum of all these three phasors IR, IY, IB will be equal to IR plus 0, 0. That is not 0. So once the algebraic sum of three phasors is not coming out to be 0, it means these three phasors are unbalanced. Lots of cases will be there where phasors are unbalanced, right? So this is one of those cases. So in this case, you will write IR again. IR, wherever you are writing IR 0, again blindly you can write IY 0 equal to IB 0. Because zero sequence components will be having same magnitude and always will have same phase. Is not it? But here you have this IY as 0. This is 0. So you are writing here 0, is not it? Procedure will be same. Just we need to put the values for various cases. In next classes, we will start actual problems of fault calculation. Just we are trying to understand the procedure that will be frequently used in the unbalanced fault calculation. So just try to understand here, right? So what will be this? This will be 20 angle 0 degree ampere. Okay, so net current in Y phase IY is 0, but its zero sequence component is non-zero. We will discuss later. Just observe. Similarly, IB0 is non-zero, although current in B is 0. So we will discuss later. Now let us calculate the negative one. Okay, we have written this IR1. Okay, write positive first, then we will calculate negative first. So this is IR, formula is same
Yes, sir.
as you have written. IR is this, and this time these two are 0. So IY 0 plus something into IB 0. This will be again equal to,
20 and
just check formula. This is coming out to be 20 angle 0 degree. So we have evaluated IR1. What about IY1? Alpha square IR1. And this is 20 angle 0. Is not it?
Yes, sir.
So you will get 20. Just check calculation.
20 and
Is coming out to be same, right? Okay. Just write IB1. Formula is same for positive sequence components. And this time alpha is okay. IR1 is for the second case. Okay, just omit this case. We are discussing for second case. So for this case, we are getting IR1 as 20.
and
So this will be
20 and
20 angle
120.
120 degree. Is not it?
Yes, sir.
So the positive sequence components of the currents are coming out to be
Non-zero.
all same. No, not same. Okay, we know that
Balance on.
these three phasors make one balanced set of phasors.
Yes, sir.
Balanced set of phasors means the algebraic sum must be 0.
Zero.
So just add IR1 plus IY1 plus IB1. So this is 20 0. This is 20 into 240. This is 20 into 120. Take 20 as common. 1 alpha square 0. Okay, fine. Balanced. Right. Similarly, evaluate for negative sequence component. Have you noted down?
Yes, sir.
I am rubbing this. So for negative, we are writing 1/3 of, we have formula IR plus, we are writing for negative, right? So 1 into IR, alpha square IY plus alpha IB. Put the values. So this will be, as IY is 0, IB is 0, so only we are having IR as non-zero, and IR is nothing but 60 angle 0. So 60 angle 0 upon this will be 20 angle 0 degree. Similarly, write for IY2, write yourself, and IB. So IY2 is in terms of IR2. Tell me.
Alpha
Alpha IR2 is not it. So that is 1 angle 120 degree. Angle IR2 is 20 angle 0 degree. So this is coming out to be 20 120 degree ampere. Similarly, this may be written as alpha square IR2. So this is 240 degree into 20 angle 0 degree. So this is nothing but 20 angle.
240.
Any doubt till now? Again we are observing that although net current IY in two phases, IY and IB in phases Y and P are 0 as fuses have been removed, but their sequence components are non-zero. See, these two are also non-zero, and these two are also non-zero. We have seen for positive sequence component also non-zero. Why so? These components do not have separate existence. These components are basically mathematical component of the current which does exist. Suppose current is not existing, so means zero. So for zero, you may write various components, like say one component is this non-zero, take another component this non-zero, take third component also non-zero. Can't we have three components? Three non-zero components of zero we have. So that's why the sequence components may have non-zero value even though the original phasor is zero, means not existing. If someone asks current in Y phase is zero as fuse is removed from this phase, current in B phase is zero as fuse is removed in this phase, but you have evaluated their components as IY0, IB0 non-zero, IY1, IB1 is also non-zero, right? IY2, IB2 are also non-zero. Why so? So you can explain it that these are sequence components, sequence also known as sequence currents or symmetrical components of currents. These are the same names, right? So these components are basically mathematical components of the current which does exist. So let us check it. As we know that IY is 0 and IY can be written, just focus for 2 minutes. So IY may be written as in terms of these components. So yesterday we have written for that also, right?
Yes, sir.
So if you are writing IY, tell me the values.
1 1.
Okay, tell me directly the value in terms of
20 angle 0. IR.
no, directly write.
IR 0 plus alpha.
So there you have IR0, IR1, IR2.
Yes.
It's not it. Okay, just remember IY0 plus IY1 plus IY2 is not it. These are the three components of this phasor,
Yes.
and we have evaluated all these three components.
Yes, sir.
So tell me the value of IY0.
20 angle 0.
20 angle 0. Okay. Plus IY1.
20 angle 240.
20 angle 240 degree. What about this?
20 angle 120.
120 degree. So this is coming out to be 0, is not it? 20 angle 0, 1 plus alpha square plus alpha. So this is coming out to be 0. So nothing is strange here, as it must be. So these three are non-zero components basically, like this. The algebraic sum of all these three components will be 0. If you are having three more or more, 4, 5, 6, you are free to choose, is not it? So no need to worry. What about IB? IB also must be equal to 0. So IB may be written as IB0 plus IB1 plus IB2. Put the value. IB0 is same as IY0, IR0, that is 20 angle 0. IB1, tell me the value.
20 angle 120.
20 angle
120.
120. So this must be 20 angle 240 degree. Just check. So this is also coming out to be 0. 1 plus alpha square. So this is coming out to be 0 ampere. Got the point?
Yes.
Any question? Solve some more problems so that you can practice more. So we will use these techniques while fault calculation.